In vector calculus, a branch of mathematics, the triple product is a product of three three-dimensional vectors, usually Euclidean vectors. The name triple product is used for two different products, the scalar-valued scalar triple product and, less often, the vector-valued vector triple product, scalar triple product. The scalar triple product is defined as the dot product of one of the vectors with the cross product of the other two. Geometric interpretation. Geometrically, the scalar triple product is the volume of the parallelepiped defined by the three vectors given. Here, the parentheses may be omitted without causing ambiguity, since the dot products cannot be evaluated first. If it were, it would leave the cross product of a scalar and a vector, which is not defined. Properties. The scalar triple product is invariant under a circular shift of its three operands. Swapping the positions of the operators without reordering the operands leaves the triple product unchanged. This follows from the preceding property and the commutative property of the dot product. Swapping any two of the three operands negates the triple product. This follows from the circular shift property and the anti-commutativity of the cross product. The scalar triple product can also be understood as the determinant of the 3 times 3 matrix having the three vectors either as its rows or its columns. If the scalar triple product is equal to 0, then the three vectors A, B, and C are coplanar, since the parallelepiped defined by them would be flat and have no volume. If any two vectors in the triple scalar product are equal, then its value is 0. Moreover, the simple product of two triple products may be expanded in terms of dot products. This restates in vector notation that the product of the determinants of two 3 times 3 matrices equals the determinant of their matrix product. Scalar or pseudo-scalar. Although the scalar triple product gives the volume of the parallelepiped, it is the signed volume. The sign depending on the orientation of the frame or the parity of the permutation of the vectors. This means the product is negated if the orientation is reversed, for example by a parity transformation, and so is more properly described as a pseudo-scalar if the orientation can change. This also relates to the handedness of the cross product. The cross product transforms as a pseudovector under parity transformations and so is properly described as a pseudovector. The dot product of two vectors is a scalar, but the dot product of a pseudovector and a vector is a pseudo-scalar. So the scalar triple products must be pseudo-scalar valued. If T is a rotation operator, then but if T is an improper rotation, then as an exterior product in exterior algebra and geometric algebra, the exterior product of two vectors is a bivector, while the exterior product of three vectors is a trivector. A bivector is an oriented plane element, and a trivector is an oriented volume element, in the same way that a vector is an oriented line element. Given vectors A, B and C, the product is a trivector with magnitude equal to the scalar triple product, and is the Hodge dual of the triple product. As the exterior product is associative, brackets are not needed as it does not matter which of a B or BC is calculated first, though the order of the vectors in the products does matter. Geometrically, the trivector ABC corresponds to the parallelepiped spanned by B and C, with bivectors AB, BC and AC matching the parallelogram faces of the parallelepiped. As a trilinear functional, the triple product is identical to the volume form of the Euclidean 3-space applied to the vectors via interior product. It also can be expressed as a contraction of vectors with a rank 3 tensor equivalent to the form see below. Vector triple product. The vector triple product is defined as the cross product of one vector with the cross product of the other two. The following relationship holds. This is known as triple product expansion, or Lagrange's formula, although the latter name is also used for several other formulae. Its right-hand side can be remembered by using the mnemonic BAC-CAB, provided one keeps in mind which vectors are dotted together. A proof is provided below. Since the cross product is anti-commutative, this formula may also be written as From Lagrange's formula it follows that the vector triple product satisfies, which is the Jacobi identity for the cross product. Another useful formula follows. These formulas are very useful in simplifying vector calculations in physics. A related identity regarding gradients and useful in vector calculus is Lagrange's formula of vector cross product identity. This can be also regarded as a special case of the more general Laplace-Rham operator. Proof: the component of is given by, or by adding and subtracting. This becomes similarly, the in components of are given by, and by combining these three components we obtain, using geometric algebra. If geometric algebra is used, the cross product B times C of vectors is expressed as their exterior product BC, a bivector. The second cross product cannot be expressed as an exterior product, otherwise the scalar triple product would result. Instead, a left contraction can be used, so the formula becomes the proof follows from the properties of the contraction. The result is the same vector as calculated using a times interpretations. Tensor calculus: in tensor notation, the triple product is expressed using the Levi's of eta symbol, and referring to the th component of the resulting vector. This can be simplified by performing a contraction on the Levi's of eta symbols, where if and if. We can reason out this identity by recognizing that the index will be summed out leaving only an. In the first term, we fix and thus. Likewise, in the second term, we fix and thus.